All right, today we'll be talking about constant acceleration equations. There are 5 kinematic variables: the displacement, the acceleration, the final velocity, the initial velocity, and the elapsed time. All our equations will be dealing with those variables. All right, but before we begin, I just wanted to point out the idea that up until this point we've always drawn all these little arrows over things. But we're going to do away with those, even though it's customary. I mean, it's more proper to do it with the arrows. It's kind of a pain in the butt to do, so we will eliminate them. So like this equation up here can be written this way without the arrows and the boldface. We assume that these are vectors, and we indicate them as being vectors by the plus and minus sign. All right, so here we go. Let's say we have an object that starts at 0 position at 0 time. And we know that the average velocity would be equal to the change in position over the change in time. But if those initial positions, initial times were 0, it could be reduced down to this. And if they weren't 0, the initials, then you would have to deal with delta x and delta t. But it's not any more difficult, honestly. So if we took this equation here and solved it for x, we'd have x is equal to the average velocity times time. And what is the average velocity? Well, obviously it is the initial velocity plus the final velocity. Add the two together and divide by 2. So that's one equation. All right, we also have the definition of acceleration, which is the final velocity minus the initial velocity over the final time minus the initial time. But sometimes we don't want to solve just for acceleration. So sometimes it's very important to have an equation that solves for other variables. I got rid of the t initial and just had t to make it simpler. If you didn't, then you can also just keep delta t in the equation. And I'm just going to solve this for v. So there's another equation. It really technically isn't another equation. It's this initial equation here we started with. Just solve for v, or the v final, because it's used so often. So there's our second equation. All right, so here we're starting with the first equation we derived, and we're going to use this to come up with another equation. And here's the second equation we derived. And we could replace the v in this equation with the v in this equation. In other words, put all this stuff in for v here. And that would give us, taking all this stuff, putting it in for v, would give us this expression. And if you look at the algebra of this, it's not really that bad. When you reduce it down, you would get this. Take a moment and look at it and see if you can understand how it got that way. V plus VO plus VO is 2VO. Half that is just VO times T. So VO times T plus the 1/2 AT squared. And that's the third expression we'll be using. All right, let's look at another example. We have a ship that starts at 0, ends at 62 meters per second, and has an acceleration of 31 meters per second squared. We want to know how long that took, distance-wise, to get from here to here where it took off. None of the equations we've derived so far will give us the answer directly. The reason is they all involve time, and we don't have time in this here example. So what we could do is we can combine two equations to eliminate time. And here is what we're going to do here. We have acceleration is equal to v final minus v initial over t. Solving for t. Okay. And we have our other equation that we derived. and we're going to take this and put it in for t. And you end up getting this. Take a moment and look at the algebra to make sure you can understand it. And a lot of times it's not written that way. It's written this way. Alright, so now we can solve our initial problem we were dealing with. We take the final speed of 62 meters per second, square it, minus the initial speed of 0 meters per second, square it, divide it by 2 times the acceleration, and we end up with 62 meters. Okay, so here is a summary of the equations we derived. If you rearrange this one, it really just comes out to the definition of constant acceleration. Acceleration is equal to v final minus v initial over t. And we'll be using these equations in the next section to solve problems.